Have you ever thought about just how dependent on the sun we are? I think about it every second of every day. What would happen if the sun died? Well, during the total solar eclipse last year, if you were standing in the path of totality, as it is referred to, within the first 2 minutes, scientists recorded that the drop in temperature was a full 15 degrees Celsius. One scientist estimated that if the sun went away completely within 1 week, the temperature would drop to 0 degrees. In 1 year, the oceans would freeze over, but not all the way through, as we got to negative 100 degrees Celsius. Because of that freezing of the ocean, it would take a long time for the Earth to cool any further, and it would get down to negative 400 degrees Celsius. At this point, millions of years after the sun died, the Earth's internal temperature generation happening inside of it all by itself would equal the amount of energy it is radiating out into space. And it would be a cold, dead ball of ice. And it'd be pretty dark on the surface. Hello, and welcome to another edition of Because Science Live, the live version of Because Science, where I take all your comments, questions, corrections, and weird things you have to say about me live off the top of my head and try to be coherent for a full 30 minutes, which is harder than you think. I have a parent voice of the void, Nate, here with me. Nate!
Yep.
Where are you?
I'm here.
Wait, where do you mean by doesn't
Just
matter?
everywhere.
Doesn't matter. Well, what we got? Let's hear from some nerds.
From Glenn McCulloch.
Sounds like a nerd already.
What is the difference between looking at the sun normally and during an eclipse? How would it negatively impact you in the short term?
You know what? I don't know. I don't know. Do they say don't look at an eclipse because there's some different effect looking at the sun when it's eclipsed versus looking at it normally? I don't know that off the top of my head. I would imagine people say don't look at an eclipse, it would hurt your eyes because most people would want to stare at an eclipse, and if you stared at the sun, it will hurt your eyes even if it is, 70% or even totally eclipsed. Just like looking at the sun directly is very bad for you if there's no eclipse. So I don't know if there's an actual distinction. I think it's just don't look at the sun, period. But if you really want to, you should wear some glasses. I think that's what's going on. But the sun is putting out a lot of radiation, not just in the visible light range, that makes it all the way down to the surface, but also ultraviolet A and B, and that has enough energy to damage sensitive tissues like your retina. And you don't want to look at the sun regardless, eclipse or not. I don't think the eclipse itself has anything to do with it physically, other than scientists know or public health officials know that a lot of people will be trying to look at it. Like the leader of the free world is looking right at it. Anyway, what's next?
From the channel About Nothing.
Prove it.
How much internal pressure would it take to explode a human head?
Why? How much pressure would it take to crack a human skull? Sounds kind of gross on the face of it. So you have here a perfect drawing of a human skull, and you have the brain case, something like that. This is completely accurate, mind you, right off the top of my head. It's amazing. I did go to medical school twice. That's a lot. So you're asking what the internal pressure would have to create inside the brain case to, I imagine, fracture the skull in some way. What would that be? It's spoopy month. Better. So what would that be? I don't know. That's these kind of questions are more experimentally verifiable. There's not really fundamentals that I could go to say, unless I knew, the material strength of bone. I can't. These kind of things are hard to estimate just right off the top of your head because you'd want to do an actual experiment. And I know of some experiments that get at something like this, where it takes a few 100 pounds of force to crack a skull open. And I knew that because I looked up how hard you'd have to press on a human skull to smash it open because of Game of Thrones. And in that experiment, scientists got cadaver bodies and they took their skulls out and they kept them wet. And then they subjected them to impacts, downward impacts with the bicycle helmets on and with bicycle helmets off, and then they also determined what was the upper limit until the skull actually gets fractured. And it's a few hundred pounds, as you might expect. But how much internal pressure would you need to crack it? I don't know. What I will say is that, and I get to this a little bit later on in something coming up, but I will say that there's enough material inside of your brain case, your brain, that if it was to turn into something like a hot gas, it could crack the skull. And we know that because it happened before. But you'll have to watch next week's vlog to know what I'm talking about. What's next?
From Will. Hey, Kyle.
Oh, hello.
I hope you're well. Is there any way Pokeballs could work successfully? What might happen to the inhabitants of the device?
Sure. So how do Pokeballs work? I did a video on this before, I think. I don't know if my conclusion would change. I kind of said it would be like how Ant-Man's suit would work. So if you were reducing, let's say, the distance between atoms by making their electrons orbit even closer to the nucleus of said atoms than they otherwise would, then atoms can get closer together and then you can miniaturize things, and maybe if whatever energy beam shoots out of Pokeballs when it captures Pokemon, maybe that kind of process could be happening, which would shrink said pocket monsters. But I mean, that's my first approximation of it. Otherwise, you would have to be, as I think it's implied with like Bill's PC and stuff like that, you're turning Pokemon into raw information, which leads me to think of kind of like a Star Trek style dematerialization, where you are getting the pattern of an entire person or organism and you're putting that into a computer, and then you're giving that to a computer somewhere else and then having it reconstituted, which in effect kills you and then makes a clone of you with your exact memories of when you teleported, so you kind of die, but then you come back to life. It's the most sciencey version of resurrection I've ever heard. Teleporters and transportation. Teleportation, that kind of stuff. So if that was happening to Pokemon, you would need a system that Bill came up with for Bill's PC to pattern all the Pokemon's information, which would be a gargantuan amount of information to get the position and velocity and energy and momenta of every single particle in their body, and the quantum states, and then store that and then replicate that somewhere else, or store all that information in a Pokeball and kind of like it's like a flash drive for Pokemon information. Sounds really complicated. Which way is better? No idea. Fictional technology. It would have to be implied somewhere in the canon, and then we'd have something to go on. I think if we go with the Bill's PC stuff, then we can go a more informational route, and then I would say that it digitizes Pokemon, kind of like Digistructing happens in the Borderlands series or something like that. How much information that would be, I don't know. I would have to estimate it, which I cannot do right now without help. What's next?
From Noni Baloney. Hi, Kyle.
Like baloney, this show is BS. You get it. Sorry.
Would bleeding in space lead to insta-death? Let's say Thor or somebody inexplicably immune to the effects of space, or a human in a few minutes prior.
That didn't sound like a complete sentence to me.
So, would bleeding in space lead to insta-death?
Now, this leads me to something I saw on a little sci-fi TV show you may have heard me talk about before. And I haven't verified this myself, but it's I didn't look it up myself, which is to say, so I might be off base, they might be off base, but I trust them. One thing I did not think about, and I don't know if NASA's ever had to deal with this, I should ask an astronaut. One thing that in space I've never had to think about is what happens when you bleed in space, like you say. on Earth, we have the omnipresent pull of gravity. And so when we get a bad wound, our blood drains out of the wound. You hold it, you hold it up, you hold it down, your blood pressure is trying to get the blood. Well, if you have a cut, blood pressure is forcing blood out of the wound, and it goes down. It goes away from the wound. But blood is a non-Newtonian fluid. It responds differently to shear forces, and as to say, moving blood layers past each other, like so. It responds differently based on the shear forces you put on it. So it flows weird. That's basically all. That's what non-Newtonian fluid means. It flows weird, and it's very viscous, and it can be sticky. So in space, if you got a bad wound, say a terribly bad wound, the blood probably, again, I don't know this, you'd have to ask an astronaut or NASA or someone. The blood is probably going to pool around that wound and form kind of like an orb because there's no gravity trying to pull it away from the body. You can see an effect like this, or hear about an effect like this, when Commander Chris Hadfield was talking about one time when he got an irritant during a spacewalk in his eye, and he started to cry, but because there's no gravity, and tears are, water is very cohesive with itself, the tears started to form an orb over his eye that wouldn't move. You can see another really cool demonstration of this when Chris Hadfield wrings out a towel filled with water in space. The water just hangs there and gloms onto itself. I suspect that blood would do the same thing and just hover in kind of like a glob on the wound, not going anywhere. And if that is happening, I can imagine that could be horrifically dangerous. Wound healing is one of the most complicated biological processes that happens inside of you, literally. And if you start messing with it, like not allowing the wound to drain or having blood pool at the surface, I can imagine that would be incredibly dangerous. I don't know if it's insta-death, but it's probably a very big instant problem, would be my guess. But again, I'd have to verify that and look into it and maybe, make an episode about it or something. Why you don't want to bleed in space. What's next?
From Dawson Wheeler. If you were in the middle of space and not close to any stars or planets,
like space.
Could you get small objects to orbit around you?
Okay, so could you have your own moons, or moons, if they even had more moons around them? Are you a large enough source of gravity to, I don't know. It's a really interesting question, though. I'd have to, so here's what I'm thinking. You're asking if, we assume you are a perfectly circular body, as all good physicists would. Do you have enough gravitational attraction to objects near you that would pull objects going by you, in effect, in a circular orbit around you, and create kind of like a mini moon? So they have some component of their velocity that is going straight, but because of the gravitational force, it acts to pull them in a circle around you. Now, you do not weigh that much. The average person on Earth, and I know some of you will be like, oh no, it's fine. It's the average. It takes into account like everyone, even children. The average person on Earth weighs 62 kilograms. Not very much. Therefore, your gravitational attraction to other objects is not very much at all. You can calculate this using Newton's law of gravitation, and you can get the force you would put on any one object. Obviously, you do not have very much, because if you were standing next to someone else, you would feel it, which would be kind of sweet. Oh, I feel something here. Anyway, so your gravitational attraction is not very much on you. Even the moons on you is not all that much. So, because the force here is not very big, the effect you can have to change the trajectory of some other object in space is necessarily going to be small. Why? Because force equals mass times acceleration. The amount To change the trajectory of an object, you have to put a force on it and accelerate that mass somehow. So if the force you are putting on something is very small, if you want to accelerate that object in a different way, in any sort of meaningful way, the mass has to be super, 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 super small, probably. So that leads me to believe that if you were out in the middle of space, as I like to say, the only objects that would be, let's say, influenced by your gravity would be the tiniest of dust particles and specks and little pieces of mass. And as we know, space is the emptiest empty of empties, as Carl Sagan once said. He didn't say that. He was better at this. In space, could there be a situation where you were in like a cloud of dust and the tiniest particles would be able to orbit around you? Would they be so small that you couldn't see them? Would they have to be microscopic? Is there enough dust in space for this to happen? I don't know. That's all an open question. But I would expect there to be some limit because of the gravitational force that your own mass would put on other objects. Those objects would have to be very, very small indeed to have any kind of orbit-inducing effect on them. That's my guess. You check it. Or put it in the comments afterwards. That makes sense. What's next?
From Wyatt Rose, besides internal bodily...
Sounds like a cool cowboy. Yeah. Just rode into town. Wyatt Rose is the name. Gunslinging's my game. What does Wyatt say?
Besides internal bodily functions, can we ever be motionless?
Besides internal functions, stuff moving around in your body, can the human body ever be completely motionless? I don't think so, because not all of your movements are voluntary. Your nervous system and things that control your body's movements are both voluntary and involuntary. For example, you can, this is a very broad example, but you can stop yourself breathing. But at a certain point, if you're holding your breath, your brain will take over and it will cause you to like that. You can try to hold your breath until you pass out. But before you get to that point, your brain will sense some kind of, hey, there's too much oxygen, too much carbon dioxide in the blood or something. And you'll involuntarily inhale. And that's kind of what causes the end stages of drowning, when you inhale that water involuntarily, and then, the rest of the bad stuff happens. So, not all of your movements are completely voluntary, which means I do not think you could ever be completely stationary because you're not in control. You're not willing everything that your body does. And this leads to kind of something related called the ideomotor effect, where even your thoughts and intentions can have an effect on your actions. The most the best way you can see this effect in action is with pseudoscience, believe it or not. Have you ever heard of a dowsing rod, which is basically just a stick? People think that this stick can lead them to water. But what is happening is that people grab onto this stick and then they just let it lead them somewhere. This can be explained by the ideomotor effect, where involuntary, almost intention-driven movements lead you somewhere. And it feels like you're not doing it, but you are, but you're not. You as an organism are doing it, but they're involuntary, and you attribute them to some otherworldly thing where it's more easily attributed to something perfectly natural, which is the fact that you can never be still ever, which kind of stresses me out. Also, it's spoopy month, I think. It's hard to tell in here, but it's spoopy month. The ideomotor effect also more or less explains everything to do with Ouija boards. When you feel like you are, what shape are they? When you feel like you are moving a planchette, I forget, around, and you're pushing it with your hands, the ideomotor effect takes over. So your intentions, what you want to happen, what you think might happen, can subconsciously lead to small, tiny movements that can be amplified by moving down to your fingertips and by other people's ideomotor effects, and so the planchette will move around the board. This The Ideomotor effect is a much better explanation than some ghost wanting to talk to you, but in a way that you understand somehow. Hey, and why did ghosts only start in 1800? Why don't we see any caveman ghosts? If ghosts really existed, there'd be 100 billion dead humans walking around, because that's how many probably existed since the dawn of time. Why don't we see more ghosts? Why are they always little girls in dresses? It's almost like pop culture influences what we think might happen, and their brain creates weird things that we see when situations that can't be explained readily present themselves to us. But what would I know? What's next?
From Evan Ho.
I blacked out for a second. Is everything still cool?
We're good.
Cool.
Can Mars have lightning storms like we can on Earth, like we see in the movie The Martian?
Does Mars have lightning storms? I don't know. I know Mars can have. Okay, so I don't want to speak outside of my own expertise. I seem to remember that Mars can have aurorae, which is like the aurora borealis that happens on Earth. I think it happens near the poles. I think. But Mars has a very, very, very thin atmosphere, just a few % of what the Earth has. And so when you do not have the atmosphere to create the same kind of weather patterns, I would guess that Mars could not sustain the same kinds of weather systems like thunderstorms could happen here on Earth. Although, again, I could be wrong. You can just Google this. So I might be wrong. Although when you have a lot of material moved by gusts of wind, etc., they can pick up an electrical charge and create lightning even in a non-traditional way. You might see lightning occurring in the plumes of volcanoes, for example. And that's because even the small particles of ash and rock, as they bounce against each other in the gusts of wind, they can transfer charge and build up charge and eventually discharge said charge in what scientists call a dirty thunderstorm, which sounds like a sex move. So can Mars have lightning? I don't know. If it does, it's probably infrequent or weird. But this is something you can Google. So I'm not going to say one way or the other. I would expect that it is less, if anything. And that, kids, is how you hedge a bet. What's next?
I'm over here.
Oh, what?
From Ookie Boogie Man.
Ooh.
How does the Ghost Rider drive his motorcycle up the side of a building?
Dude, I don't know. I can't explain anything that Nick Cage does. Can you? Actually, I can. It's money. Anyway, it's okay, he's not watching. How would you drive up the side of a building, let's say? Well, I mean, I think the most realistic example of this you see in Batman and Robin? Forever? Anyway, at one point in one of the movies, Batman's Batmobile drives up the side of the building, and that is because he fired a winch straight up, and then it pulls him straight up the wall. That is the problem at hand here. If you have a wall like this, Batman's Batmobile wants to go up it, he needs to put this kind of force on his Batmobile, something to take the mass and accelerate it like this and go up. What's fighting him is the acceleration due to gravity, weight. That gives the car weight. The problem, I would guess, with something like a motorcycle, when you don't have a winch, is that the force that your wheels can put on a wall, especially when it is vertically oriented, is that the reactionary force from the friction on your tires is much, and I'm not drawing it to scale, is much smaller than your weight. And so it's not going to be able to take you up the wall. And even if you increase the frictional forces a lot more, the tires. This is not a perfect interaction. The tires are and the engine, and if you're sitting on a motorcycle, your own weight is going to act like a moment, because you're holding onto the handlebars and you're leaning back as you're going up. So that's going to act like a moment to pull you off of the wall rotationally, and that's even more work that the friction would have to do, and you need a balancing force this way as well now to counteract that moment and all of this. So going up on two wheels up a wall, I think may be darn near impossible. Well, unless it was, see, this is the frictional problem, right? If your wheels had spikes in them and creating a heck of a frictional force, both upwards and into the wall, so that even leaning back, because the spikes are going into the wall, they act to not want to be pulled out of the wall, which is just friction. And so you have two forces that would allow you to get up the wall. But just a plain motorcycle, no spikes, sitting on the back, I think it'd be dang near impossible. However, there is a way for cars to drive on non-traditional surfaces. And I've said this before, of course, and you may know of it, but in theory, an Indy car can go fast enough so that it will, perfect Indy car, so that it could drive on the ceiling. And that is because at some point it can be going fast enough that it creates a downforce on, because of how it's shaped, it creates a downforce from itself passing through the air. It creates a downforce that's kind of like reverse thrust, I guess. Anyway, creates a downforce on it that is greater than the car's weight. And so then in theory, and I know I've talked to Adam Savage about this actually, and the reason they've never done this is because they could not find a wind tunnel that wasn't, $10,000 per hour and an Indy car that's, $1 million to use. So they never actually did this. Anyway, in theory, this is totally possible. The downforce at speed at like 150, 200 miles an hour, what these cars go, some of the fastest things we've ever made. The downforce is even more, it's not only equaling the weight, it's a little bit more than the weight, so it's stuck on there. It could keep going. What are we talking about? Yeah, Ghost Rider, Nick Cage. Probably not. IndyCar on the roof? Theoretically possible. What's next? I think we have time for
last one.
Last one. Why is that?
From Johnny DeBucha.
Ooh.
Johnny DeBuncha.
Sure.
What is your favorite equation?
I don't know what my favorite equation is. I don't want to pick favorites. They don't care. But the equation I use the most would have to be kinetic energy. I use kinetic energy more than just about anything. It is so, and this is the equation for it, and it is so useful. I've even spent I've gone home. I mean, as much as you can call this a home. But I've spent hours at night just deriving this from first principles just to see if I could, because I liked it so much. And because it's so versatile. From kinetic energy, you can start working with the concept of work. From that, you can get forces of impacts. You can get energies. You can get powers from that energy. It's a very, very versatile equation that is very good at doing the kinds of math that I do on this show, which is impacts and forces and momentum and stuff like that. It's a all-purpose kind of thing, and I like it a lot. And you should too. Please. And that's all the time we have for this episode of Because Science Live. Thank you so much for joining me all this week. A lot of you have a lot of things to say about the teleportation episode that I put up yesterday. That's great. Put them in the comments. I'll look at them as best I can, and I'll answer as much as I can on next week's vlog. So next week, we have a new vlog, we have a new episode, we have a new live stream. I hope you'll join me because next week's episode, you're gonna love it. I swear. So if you want more of me, you can go back to the channel, subscribe, hit that notification bell. You can check me out on facebook.com/BecauseScience or at BecauseScience on Instagram and Twitter. Or you can go to alpha at projectalpha.com, where if you sign up for a free trial, you can get this show 2 days earlier than anyone else, and you can start planning those super nerd comments so I can point them out. Have a wonderful rest of your weekend. Stay spooky, and remember, be nice to each other, because this is all we got.